sixth edition of our Numerical Method 2 class. First of all, I would like to apologize for starting 10 minutes late because of internet connection problems. So I asked the class representative to inform you that I was facing connection problems, so I couldn't connect. And I've been trying for the last 10 minutes before, maybe the last 12 minutes before I succeeded to connect. Okay, so without any further ado, we will proceed with what we tackled yesterday. Just to quickly recall what we did, we derived the formula that allows us to find the coefficient of our rational function Rx. We saw that when we write our rational function in this form, there is a total of capital N plus 2, where capital N is the degree of this rational function, and the degree is what? The sum of the degree of the numerator plus the degree of the denominator. So that's what gives us capital N. Now plus 2 because each polynomial has its number, the number of coefficient in a polynomial is the degree plus 1. So that's why we have n plus 1, which gives us the degree of the polynomial plus 2. And we saw that this degree can be reduced by 1. Since the denominator cannot be 0, we can assume that Q0 is not 0. And for that, we factor both the numerator and the denominator by Q0, and we cancel out. If we do that, you see that the coefficient here will be 1. So we can assume that our Q0 is always 1. By so doing, it allows us to reduce the number of parameters by 1, which is not negligible, right? Now we design an algorithm that allows us to compute these capital N plus 1 coefficient. And for that purpose, we computed the difference between F and Rx. That is in fact the error. This is the error. That's the error. This difference is the error. And we impose the fact that 0 has to be a root of multiplicity capital N. Capital N plus 1, sorry. Multiplicity capital N plus 1. So for that purpose, we impose that the k derivative at 0 of the difference at 0 for k running from 0 to n is 0. And if that is the case, this has a consequence. And the consequence is that in the denominator, in the numerator here, because if you expand this, right? If you expand the numerator using Maclaurin, if you take the Maclaurin series and substitute into the expression of f of x, we get this. So you can expand the entire numerator as a series. So if we expand the entire numerator as a series, we know that for this to be true, it has to be true also for the numerator. Because remember, if you set a polynomial of this to be 0, it means that it's the numerator that is also 0. Similarly, if the multiplicity is n plus 1, it means that in the numerator, the non-zero term should start from capital N plus 1. Consequently, we can set the numerator to be 0 for all the coefficients k running from 0 to capital N. That's what gives us our linear system. Because we obtain a linear system in n plus 1 equation in n plus 1 unknown. And therefore, it is a consistent system that gives us a unique solution for the parameter P0 up to Pn, Q1 up to Qn. So that's how we succeeded to obtain an algorithm that will allow us to compute the parameters P0 up to Pn and from Q1 up to Qm. And in the process, we show that in order to set this to be 0, for k running from 0 to capital N, we need to find the coefficient of xk, where k runs from 0 to capital N. And for that purpose, we just expanded this expression and group all the terms, and we saw that the coefficient of xk is given by this formula. Now, if we set that to be 0, then we can take negative p to the right-hand side. We obtain this boxed. You can see this formula box in red. That's what we obtain. So we have a total of n plus 1 equation in, n plus 1 unknown. Okay, now bear in mind that in this expression, you have to bear in mind that because the coefficient of Pn, because the polynomial P, which is the numerator of Rx, has a degree n. So, but since k here will exceed n, in the formula, each time P k will appear for k greater than n, that p will be set to 0. Because if you look at the expression of p here, p exists up to pn. So if we have the subscript of p to be greater than n, that is set to 0. Let me repeat what I'm saying. I will repeat it on another slide for you to understand properly. This, you can see this imposition, this one. So what I will do, I will rewrite this formula in a new slide and proceed with the explanation so that it will be clear once and for all for everyone. So we saw that the equation that we'll be solving is the following. We'll be solving this linear system, I running from 0 to k, a sub I, where a here are the coefficient of f of x. Because f of x is a function that we are trying to approximate using a rational function. And q are the coefficient of the denominator. Okay, now if you set this to be 0, so we take this negative pk to the right-hand side and we obtain equal to pk. Now you see that our k here run from 0, 1 up to capital N. But don't forget that capital N is larger than, capital N is greater than N, N, N and N. But we know that this pk will be non-zero, or most of them will be non-zero, or they exist for k running from 1 to n. So when we exceed n in this formula, you can see that in the formula we still have pk. But we need to bear in mind that from P1, because this pk exists for k taking the value 0, 1, up to n. So, which means that in this formula, okay, let me call this 1. In equation 1, so in equation 1, so this implies, so this remark implies that in equation 1, because in equation 1, when we will vary k, once k exceeds n, that is for k equal to n plus 1 or up to capital N, we will still have pk in the formula, but those are set to 0. Pn plus 1, because they don't appear in our polynomial px. So these in this formula, because they will appear in the formula, they will be all equal to 0. Because they will appear in this formula, but they are all 0 because Pn plus 1 does not exist in Px. Because Px is what? Is P0, P1x up to Pnx to the n. So this is our Px. But in the formula, when you take k equal to n plus 1 in this formula, you will still get Pn plus 1. But that Pn plus 1 will be 0 because it does not figure in this formula. It's not there, it's not present. It does not exist. So we set all these coefficients to 0. So we do the same thing for Q, because Q will stop to Qm. But because k takes the value up to capital N, it means that that m will be exceeded. So similarly, Q, K, whatever will be there, exists for k equal to m in this formula, because k equal to 0, q0 is 1, right? Okay, let me put 0. You know that q0 is 1 up to m, like that. So similarly, in equation 1, we would therefore set any other coefficient q that will appear in this formula, that is q m plus 1 up to qm n q capital N, they will all be set to 0. So therefore, I repeat once again that this is the formula you need to keep in mind, because out of experience, okay, let me close this one. So out of experience, people who try to expand this expression and put it in this form usually get the wrong result. So this is just because you see we have already done that expansion here. Here, you can see here, we have already expanded this to reach to this formula. So you don't need to repeat this each time you solve a problem. You don't need to repeat this all the time, because some of you, when you be expanding, you will not bear in mind that all the terms of degree less than or equal to n has to be set to 0. You will not bear this in mind. You will just take whatever coefficient will appear according to your computation. You will just put it in this formula, which will be wrong. So that's why I'd advise you to use this formula and bear this constraint in mind. Bear this constraint in mind and use this formula directly. Don't try to expand this again, because by trying to expand, you might make mistake. And if you make mistake, all your result, I say all, and you will get 0 because nothing will be correct. If you are not convinced, I advise you to do this problem, expand it yourself, and do the same problem by using this formula directly, assuming this constraint. You see that you get this system directly. Directly, you get this system. Whereas if you try to expand this, because remember, some of you might not even stop to x to the 5. Some of you will even add x to the 6. And they will not bear in mind that, no, because our capital N is 5, I don't need to have a coefficient, x to the 6. X to the 6 should not appear. X to the 6 should not appear. You can see here, it's only up to 5. So when you expand this expression, let me take, for instance, this x5 times this should not appear, because if I multiply x to the 5 by 24, 120, if I multiply it times q1x, you see that the coefficient of x will be x to the 6. That coefficient should not appear. I should not put it there. But some of you might keep it in the formula. And if you keep it in the formula and you equate with the right-hand side, you will get the wrong result. So that's what I'm saying. In order for you to avoid this type of mistake, it's better to use this formula directly and impose this constraint. If you do that, you get this directly without the need of expanding and identifying this term and set them to equal to p and the other one to be 0. I think with practice, as you practice, you'll be able to understand what I'm explaining. Okay, now let us tackle this problem, because that's where we stopped last time. Okay, so what I would do, I will use this formula. I will use this formula, this one, with this problem. I will try to solve it. I will not go through this because you can do that yourself. You can do this. Or if you want, let us expand. Let us expand. Okay, so we set this to be 0 because this is equal to 0. If we set that to be 0, we can put the equal sign here. So we can write that this is equal. This is equal to that. Now we expand this. So let me expand it below here so that you all see. Now in the expansion, how will I proceed if I expand this? But I advise you not to do that, right? But if you are comfortable with expanding, do it. But I don't advise you to do that. But some of you might find it more convenient. So I will not impose it. Okay, now we take this one, we multiply with each of the terms. You see that x will not, the degree of n of x, the degree of x here will not exceed 5, because remember that in this case, our capital N is 5. So in this expansion, I should not obtain x to the k where k is greater than n. So this should not happen. x to the 6, 7, and upwards should not appear. It should appear from x0, which is a constant, up to x5, but not more than that. Okay, now if I take 1 and I multiply, you can see that this is x to the 2, which is less than or equal to 5. So I can copy all this. So for 1, multiply by this entire expression, I just copy and write everything. Q1x Q2x squared for 1. Now, if I take x, the highest degree, well, if I multiply each by x, it will be x to the 3. So I can write everything without any problem. So plus x plus q1 x squared plus q2 x cubed. Right. Now, if I take this one, multiply throughout, the highest degree will be x to the 4th, which is less than or equal to 5. So I can take everything. So I will expand blindly. So plus 1/2 x squared plus q1 by 2 x cubed plus q2 by 2 x4. Now for this one, if I multiply throughout, the maximum will be 5, so it's correct. I can use this and multiply throughout. So I will continue here. Plus x cubed to this by 6 plus q1 by 6. Oh, okay, q1 by 6 x4 plus q2 by 6 x5, and that is the last expression. Now I come here, and this is where you have to be careful, because if I multiply throughout, you see that the highest will be q6, but I don't need x to the 6. I don't need that one, because I say that xk, where k is greater than 5, should not appear. But if I don't stress on this, some of you, when you expand, you see keep it and equate, and it will give you wrong result. So that's what I'm saying. If you are not comfortable with the expansion, don't even try. Just use the formula and substitute the result. But if you can obey all the rules and you are sure you will not make a mistake, then it's fine, you can expand. So let us do that. And now for this case, we have x, or 1/2 by 24 x to the 4th for this first multiplication. Now this times q1x, that will give us q1 by 24 q1 is already there, by 24 x5. That's for q1, but I cannot multiply this expression by q2 x squared. It will exceed, so I drop that term. Now the last one will be this one. I will take this and multiply by this only, because if I take this and multiply by q1, it will exceed 5. It will be x to the 6. So for this last term, I will only multiply by x1. So plus x to the 5 by 120. Okay, now you can see that this is an expansion. Some of you might even add x6 to the something. You don't need it. You don't need to add this term, because if you multiply, it's exceeding already the 5. So there's no need to add this extra term explicitly. You can just put the ellipsis to indicate that this is a series. But in your computation, you only stop here. You don't need all the terms that appear after x to the 5, because your maximum that should appear in your formula is degree 5. So that's why this term is not necessary. You don't need that one. So we only stop here. So the terms after are not important. So this is what you have. After expanding, so we take this equal to the right-hand side. And what is our right-hand side? This is P0 plus P1x, P2x squared, P3x cubed. Now we group all these terms, right? We group them because this is a polynomial of degree 5. So we group all these terms. Oh, sorry. Yeah, it's up to 3. Okay, it's fine. Now, I will group all these terms from the constant term. Okay, the constant term is only 1. There's one constant term, which is 1, this one. Now, I look at all the coefficient of x. So the coefficient of x, I have this x. Okay, so I have this x. So it will be 1. And then I have this one, q1x. So the coefficient is q1. Now, do we have another coefficient of x? No. These are the only terms in x, right? The other ones are greater than x. So I factor by x. Now let us take all the coefficient of x squared. The coefficient of x squared, so if I look throughout, so this is 1/2 x squared. So I have 1/2 there for this one. Another x squared is this one, which is q1. Other x squared is this one, q2. This one. Plus coefficient of in x3. In x3, we have this one in x3. What else in x3? X3, we have this one also in x3. So this is 1/6 for x3. Okay, these ones are greater. Then we go down. We have this one, this term, q1 by 2. So q1 by 2 is this one. x3, another one is this one, q2. And that's all, x cubed. Okay, so the next term is the term in x to the 4th, right? X to the 4th. So we look at, let us look at the, okay, everything here has been selected already. So this is x to the 4th, this one. This is another one, okay. We have this one, 1 to the 24th. 1 by 24 is this one. We have this one, plus q1 by 6 plus, okay, another term, okay, this one q2 by 2 plus q2 by 2. Okay, I think that's all for x4. Now we look the terms in x5 plus the factor of x5. So everything here on top have already been selected. Okay. So you have this one and this one. So these are the two in x5. So it is 3. We have 3 terms. 1, 2, 3. So this one, the constant term, this one, 1 by 120, 120 is this one, this term. The next one is the one in x in q1. So this one plus q1 by 24 plus the last term is this one, q2 by 6 x5. So you see that all the terms have already been grouped. All the terms here on the right, on the left hand side have been grouped. So we equate this with the right hand side, which is p0 plus p1x plus p2x squared plus p3x cubed. Now you see that two polynomials are equal if and only if their respective coefficients are equal. Okay, now this is a polynomial of degree 5, and this is a polynomial of degree 3. So if we want to equate two polynomials of degree 5, we can extend this. So this will be 0 times x4 plus 0 times x5. You see? Okay, now this is the p. This is our p. P4. This is our p5. In this formula, remember, we said that in this formula, we will set all the p's. Oh, sorry. We said that we will set all the p's greater than the degree, which is 3 in this case. So we take p4, p5, and we set them to 0 in this formula. That's exactly the same thing we are doing here. We are setting this to 0 in order to equate. And similarly, in this formula, you see that when we will take, okay, what is the degree of our, let me check the degree of Q first before I explain. The degree of Q is 2. So meaning that Q3 and Q4 will be set to 0. Now in this formula, when K will be equal to 3, right? Because remember K goes to 5. So K will take the value 3, 4, and then 5, right? But here it stops at 2. But now in the formula, when K will be equal to 3, I will take the summation here up to 3. Now when I will be 0 here, when I will be 0, Q K minus 0, K equal to 3, you see that we have Q3 in this formula. In that case, you have to impose that Q3 is 0. Because if you don't do that in this formula, in your expansion here, you'll be having Q3, Q4, and you have to set them to 0. So that is the explanation that I gave to you with respect to this imposition, this one. What is it? This one, this line. That's what it means. Because when you are expanding this one, you get the values of Q and P that will exceed their degrees, and you have to set them to 0. But if you expand this directly, those Q will not appear. They will not appear. Right. Okay. Now, if we equate, so we equate, okay, this is the constant term. We will say that P0 is equal to the constant term here. So when we equate, we get P0 equal to 1, or 1 equal to P0. So we equate this with this. Now, the coefficient of x will be equated. You see, the coefficient of x here is 1 plus Q1. So we say 1 plus Q1, which is the coefficient of x, will be equal to the coefficient of x on the right-hand side. So that is equal to P1. So that's what we will get here. So now, for the coefficient of x squared, is this one. So we also put 1 half plus Q1 plus Q2 equal to P2, which is this one. So, okay, let me proceed with the other one. So we also write 1 by 6 plus Q1 by 2 plus Q2, which is a coefficient of X3 equal to P3. Right? Similarly, we'll write the same thing for this one. Now, the coefficient of X4, which is 1 by 24 plus Q1 by 6 plus Q2 by 2 is equal, the coefficient of X4 here is 0, so equal to 0. And finally, the last one, the coefficient of X5, which is this one, will equate 1 by 120 plus Q1 by 24 plus Q2 by 6 equal to 0. So that's exactly what we get here. You see. All right, so once you write this, you already have the value of P0. P1 depends on Q1, P2 depends on Q1 and Q2. So we have this, but we need to get Q1 and Q2, and there will be, sorry, and we also have this one, P3. P3 will also depend on Q1 and Q2. So we need to solve a system in Q1 and Q2. In that system, you can see that we have two unknowns in the Q's. And for these two Q's, we have an equation equated to 0 to solve for Q1 and Q2. And this comes from this extra term here, where we set P4 to 0 and P5 to 0. That is what gives us a right-hand side or left-hand side, depending on how you write it. And then we can take all these coefficients to the left-hand or right-hand side to obtain a linear system for our Q1 and Q2. So once we solve this linear system in Q1 and Q2, we come back and substitute in the formula to obtain the values of P1, P2, and P3. So that's the procedure. So if you are confused at this stage, even if you get the correct equation, you might not get the correct answer, because some people, once they reach here, they will want to solve this. Never solve the equation where P appears. You can express P in terms of Q's, right? And then solve the system in Q's. That is the procedure. You always solve the last system that will be equated to 0 in this expansion. It will give you a linear system. You solve first that linear system in Q's. Once you get all the values of Q's, substitute back the values of Q's to get the corresponding values of P's. So that's how you proceed. Okay, now let us continue. Let us proceed with our equation. So from this, we first solve this, right? We solve the linear system. It's a system of two equations in two unknowns. So once you solve this, you obtain Q1 is negative 2 by 5, Q2 1 by 20. So once these two values are obtained, by solving this, you can use Cramer's rule. You can use substitution. It's up to you. No method is imposed. You can even use Gauss elimination if you want, right? Of course, Gauss elimination is if you have a 3 by 3, a system of 3 equations, 3 or none, or over, right? Or a larger system. You can use a Gauss elimination because it will be faster. Okay, now you can take these two values, substitute, of course, Q1, you can substitute Q1 into the first equation for P1. So you obtain P1 is equal to 1 plus Q1, which is 3 by 5. If you substitute this value, the value of Q1, you obtain this. So for P2, which is expressed like this, So you substitute these two values into the expression of P2, you obtain 3 by 20. And similarly for P3, you substitute Q1 and Q2 in this expression, you get 1 by 60. So this is the procedure, and this is the order in which you will solve this system. You first solve the system in Q, and once you get the values of Q, you substitute into the expression of P's, into the P's, and then you get all of them. And once you get these coefficients, substitute them back into the expression of your Rx, because remember, our purpose is to compute Rx. Substitute that into the expression of Rx, you obtain this. So roughly speaking, that is the methodology. And this method is what you call per-day approximation. The algorithm is the per-day approximation. This procedure is our per-day approximation. Okay, now, if we compare, here we are going to see the comparison. In this table, we compare the exact value of the polynomial, which is this one, because this is what we are trying to approximate, right? X e to the x, because that's our f of x. Now, we will compute all these values at this point, x equal to 0.1, 0.2, 0.3, up to 1. These are the values of exponential x for x equal to these values. These are the corresponding expression of exponential x. Now, P5, that is, if we approximate exponential x using a polynomial of degree 5, this is what you get. Now this is R5. That is the rational function of degree 5. This is what you get. Now we compute the error. This is the error. We take exponential minus P5. If you use a polynomial of degree 5 to approximate that, this is what we get. Now, if you use Rx to approximate exponential, this is what we get. Now we can compare these two. Now, if you look at the table, at these two columns, this one and this one. So if you look at the various results, you see that this one gives you a better result, right? For instance, look at this one. You can see that this is 10 to the 3, 10 to the 4, 10 to the 4, but here already we have 10 to the 5, right? And this one, at this level, if you compare, this is 10 to the negative 6, this is 10 to the negative 7. 10 to the negative 6, 10 to the negative 7. Here you have 10 to the negative 5, here you have 10 to the negative 6. So this one gives you lower error here. And the best way to quantify that is to compute the 2 norm. You can take the 2 norm of this, meaning that you take the global error, because these are local errors. You can take like a kind of global error, take the 2 norm of this column and the 2 norm of this column. You see that the final result will give you a lower error here in the last column, which indicate that per-day approximation gives you a better result compared to polynomial approximation. So this is one of the motivation. So if you want to approximate, instead of using polynomial, because I told you that polynomial are not good to approximate function at points. But with this experience, I can already tell you that it is better to use the per-day approximation compared to the polynomial approximation, right? Okay, so as a homework, I will ask you to compute these 2 norms. So homework, compute P5 minus F two norm. When I say f is this one, exponential x, right? So from this table, of course, when I say compute, this is from this table. We will use this result to compute. And R5, of course, it's R. We wrote there R, but it's R5, in fact. R5. So R5 minus F. You can use the two norm, you can use the infinity norm. You can use either the two norm, the infinity norm, and compare them. Compare the result and compare. The results. So you will see that the second error will give you a good approximation compared to this one. Okay, so we will stop here for today. If there's any question, we still have 2 minutes before the end. Is there any concern, any question you want to get? I mean, you want to ask a question because maybe you did not understand something. You have the floor. Is there any question? So far, so good. Kashupi, you are not saying anything.
Sir, I don't have any question.
Sorry?
I don't have any question.
Okay, thank you, thank you. Anybody else? Okay, so if there's no question, we will stop here for today. Thank you for your kind attention. God bless you and see you next time. Bye-bye.